very good morning to all of you. Thanks a lot for taking your time out on a Saturday morning and choosing to join us on this session. Myself, Rajesh. I'm a co-founder and head of products at Doppelio. Doppelio is building a first of its kind test automation platform for IoT applications. This, specifically focused on the IoT applications area. Prior to joining Doppelio, I was heading the digital agriculture portfolio for Bosch. Wherein I was working with multiple teams on using sensors, drones, and satellites to be able to build a platform that helps very large-scale commercial agriculture companies to change their business economics way beyond what they are able to do today. So in doing so, the idea was to capture data in real time or near real time from the field, process them, and apply AI to be able to take real time point in space specific decisions, so that the companies can apply precision agriculture techniques to do different kind of optimizations on different points in the process within the field, outside of the pre-field, etc. So the main aspiration was that to change these latest technologies and buzzwords to be able to change the business economies, the business models, and help out the customers, right? But then what I realized while working with the technical teams, right, as business teams, we want to change things tomorrow. If we build the solution, it gets launched, used by hundreds of customers, and then they are able to reap the benefits tomorrow. So that's how we think. But then in getting all of these, kind of solutions into production, whatever vision we had from the business side, I happened to work with teams that were dealing with, sensors, audio, video, data, and then people who were working on AI, etc. And when it comes to making these visions real, the kind of struggles that they go through is extremely, high compared to the way we emphasize as we talk, right? So each of these teams, they would go about taking an initial hypothesis, stitch together a solution because everything is innovative, and then they will test it on their, limited setups what they have. They will release it to the production. So the idea is that we really make one release and then we keep iterating it like a mobile app or a web-based application that we build. And then when these solutions get released, we would have tons and tons of feedback, not even from the production environment, even from the the field testing or the user acceptance testing phase. We will have tons and tons of feedback coming in, and then we go back to the drawing board and start solving that. If you look at that whole exercise that we were going through, we realized that was extremely unoptimized from the perspective of the amount of wastage that we were creating, right? Not because just because we are not able to really test out all the things that we are building on the lab. So everything had to have feedback from the field, because all the IoT solutions are dealing with the physical infrastructure, the physical hardware, etc. But it's an agriculture solution, we need to deploy it on the field and test it out. So that it was extremely hard, and it was from a business perspective, that is not something that I wanted to do. So I was grappling with all that kind of problems and looking forward for a perfect solution that could help us out beyond what we were able to do in house. And that's when I happened to join some of my partners in crime. I have three other partners at Doppelio, Garo, Shamila, and Shini, who were experimenting and doing business of IoT from different perspectives. So they were building smart building solutions, they were building smart surveillance solutions, connected factories, etc. in different capacities. Garo from a business perspective, Shamila from engineering perspective, Shini from solutioning perspective, so on. And one common thread all of us had was, man, this is difficult. It's easier to sell IoT solutions. It's all aspiring visions that we are able to sell. But when we want to release these solutions in production, it's a nightmare, right? So that's how we all came together and said, okay, there has to be an innovative way of solving this problem, this complexity of building, validating, and rolling out IoT systems into production. That's how the Doppelio was born. And we were fortunate, to start with a company like Bosch through their accelerator program, and then eventually participate in a supplier engagement, etc. So that's kind of a context, right, where I come from and why the context of IoT, and especially the validation of IoT solutions, is extremely important from the perspective of launching and running IoT businesses. So going on, as I said, right, people like me and you in our companies across the board, any company that I know of in any scale, everybody aspires to do a connected and intelligent product and change their business models, the way they earn money, the way they work with the customers, etc. And when it comes to reality, if you look at statistics from companies, consulting companies, etc. Only about 20 to 25% of these actual IoT projects see the light at the end of the tunnel, whereas the rest of the 75% do not scale beyond a POC, because it's all easy when you stitch together a couple of devices, collect some data, do a good dashboard. So it goes up till there. But when it comes to crossing the chasm and getting into a real field deployed solution, 75% of them lose out, which means 75% of people who are backing those solutions actually lose out, day in, day out, which is not an ideal thing to have. And even for the solutions that are getting launched, so what is happening, right? While we are just scratching the surface of this connected and intelligent product world, we already see a lot of news coming in the press. If you see, product launches getting delayed. The most popular one in the recent days have been from the automotive one, because the automotive is a big believer of connected and software eating the car realms, etc. Starting with the Tesla moment that happened. So you see product launches getting delayed because people find out defects in the last minute, all pointing to the software. Second, it crosses the launch cycle, gets into field, but then there is a lot of recalls happening, again pointing to software issues as we move forward. Just not in the automotive, it is in the consumer side, right? Companies like Nest, who is launching a consumer electronic product. There is a smart lock product which didn't work properly, so people are getting locked out of the house in a very cold environment, etc. So all of this is what we see in the field, and what that means to the companies that are behind this product is essentially, it's a lot of wastage of money. It's a point of losing customers, and in some cases it's a matter of battling big legal suits that can lead into heavy penalties, right? And ultimately it's all this, the delayed launches, product recalls, unhappy customers, and in some cases the loss of life, which happens to these companies. And so the obvious solution, so what could they do about it? It's fairly easy, because we have been building software for decades now. So they need to be tested comprehensively and very, very early in the development cycle. But that is easier said than done in a connected connected solutions environment. And what we see happening is people trying to do the comprehensive testing, people trying to test, but it's just not comprehensive and early enough. So 50 to 70% of actual testing happens on field trial. So I sit and develop my product, be it a waterfall development model, agile development model. I code my software for some time, and then eventually I allocate a certain time period, few months, few weeks, whatsoever, where a lot of these validations has to be done on the field, which means if I'm testing a connected vehicle, I drive around the vehicle miles and miles, try to validate things. If I'm testing a connected building, I roll out the solution in a very small scale and then start figuring out things. And a lot of feedback and the results that come out of these experiments is extremely surprising for the folks in the development and architecture side, leading to high cost of fixing those defects, because it leads to sometimes changes in the core itself. In an ideal world, the testing on the field should be about less than 20%. The rest of the 80% of the validation should ideally happen in the lab. So you can do it in a much faster phase, in a much economical manner, as well as in a more comprehensive manner, because you can handle, control things around from a testing standpoint. The problem with field trials is that okay, I'm afford to spend the money that it takes to get this validated. So the problem is, even if I'm able to afford the field test, the testers are not able to control the test parameters, right? I want to test the smart building for fire. I cannot really set a building on fire and test for that condition. So it's extremely hard to test these IoT solutions because of the necessity to control the physical environments, the necessity to control the physical devices, as well as the network conditions associated with it, etc. Right? Now the options that people have are inadequate, time-consuming, and costly. And so that's where we came up with the concept of saying, okay, so the best option would be to use the virtual test beds, which is not new from the software testing perspective. People like safety critical systems, people who test high-end automotive systems, they have been using virtual test beds. So which means we should be able to learn from those concepts, add on additional infrastructure and the capabilities that are required from a connectivity perspective, and then do the whole thing for the connected solution as well on a virtual test bench, right? So now if you want to see the contrast, if you look at the current slide, this is a typical view of an IoT test environment wherein I have a gateway device, one or many of them, that is getting connected to the physical assets. It could be a car, truck, or it could be a building. And that device is gathering data from the field. It is publishing the data to the cloud, and then magically some decisions are taken. In some cases, the decisions are being passed on to the human beings, and human beings act on it. And in some cases, the devices themselves act on it on an automated fashion. For example, okay, I see a fire, call the fire brigade. I see an intrusion, call the security, so on and so forth, right? And the way people test it, at one side, as I said, is the field testing, where you connect the device on a vehicle, drive it around, connect it in a building, test it out, where you have the limitations of being able to control the test parameters itself, not possible. So the other extreme, what people do is that people build test benches. Test benches could be a hardware in loop modality, where the hardware itself is connected to a simulated test system that allows the tester to change the inputs, etc. Or it could be a software in loop kind of an environment where everything is software, and then I'm taking a software components from my device and then fitting it there. But if you see the extremes, on one side, I could not, one is costly and it was time taking from a field test perspective. And when it comes to test bench, what we saw in our environments as well as what we see from our customers' perspective, building and managing a test bench is easier said than done, because you have limited set of resources that you want to invest in engineering, and you are better off investing that the resources that you have on building your core product than building a test bench that tests the product, right? So that's where we see our customers struggle. So we said, okay, so we will standardize the virtual test bench, the test bench that people are trying to build. And then because the testing it with the hardware and a hardware in loop kind of environment is extremely hard to manage, as well as time taking and cost not viable in most cases, we took a completely 100% software driven approach. So we said, in a real testing environment, people are trying to connect the physical devices to the cloud and test it out. We replace those physical devices with virtual devices, what we call Doppels, which in German is the word for twin, right? So we said, you virtualize the device, so you have a 100% virtualized device. If you are testing a car, you've got a virtual car. If you are testing a tractor, you've got a virtual tractor, etc. Now, once I have the device virtualized, then the next logical question that the tester would ask is, what do I do with those devices? I want to put them in different test environments. I have this building, which is virtual, but I want to put fire in it and then test it out. I want to put it in a intrusion condition, test it out. So that's when the next component comes into play, which is a simulation engine that lets the tester to create simulated test scenarios around the virtual devices and test it out. So what essentially happens, I have a virtual device, I have a virtual test scenario, and when I execute them, all of the virtual devices talk to the application on the cloud. So the guy could go out and validate for whatever thing that he wants to validate. But there are a couple of catches in it, right? It's not, again, as trivial as what I told. When you took this approach, when somebody talks about virtualizing a device, then the device has things about, oh, I need to know the physics and chemistry of the device, so I can use a product like ANSYS or MATLAB to kind of create the virtual device. And also, I need to write a lot of code to write the simulated scenarios around that virtual device that I created, which means I'm investing more or less equal to the kind of resources that I need to be building my product. So not easy. The second biggest disadvantage with just stopping here is that the testers who are testing and validating these connected solutions, first of all, they are not domain experts. They don't know the physics and chemistry of the the hardware and the environment that's going through. What they know is the specification of the software that is running on the device, as well as the cloud and the boundary conditions that the device works with, the data that they deal with. That's all they know. Second thing, again, we have a lot of testing still being done in a manual fashion. So there are a lot of manual testers who cannot write code. Second, even if they are able to write code, they can only do after they stabilize the test itself, after the test development test phase is over. So just saying, I will create a virtual device and using simulation scenarios is just not going to be viable. So that's when we realized that all of this has to be done in a very, very low code fashion, targeted at an application tester, which means a tester who does not know the physics and chemistry of the device as well as the environment, as well as does not want to or have to do a lot of code as the product gets developed, can easily use the virtual test bed without really worrying about all of those things that I talked about. So in case of the product that we are building, Doppelio, so the primary interface for the tester is a web UI where he can go create the virtual devices as well as the scenarios, everything by doing a point and click, right? In the matter of minutes, he has got the whole stuff configured. But then there is this other question, right? When we talk to people, you can do all of this using the UI. But then they said, oh, that's good to start. I'm building my test. I'm validating it, but I want to do the regression testing in a completely automated fashion. So then we said, you know what? Okay, everything that you are able to do in the UI, we give you APIs. So which means if you are able to execute a test using UI, you can also do it so using an API. So you can run the same test. So now what happens when I execute a test in the virtual test bed? The virtual devices get created and they start pumping data for the different scenarios which this guy has stitched together to the cloud. And when these devices are pumping data, the guy would go to the cloud application. The cloud application from a testing point could be characterized into three things. One, it could be showing some outputs on the mobile app in terms of the alerts, in terms of the data dashboarding, or it could be a web app, or it could be something deep down in the stack, some decisions with the AI is making on the platform level. So these are the things that the guy needs to validate when the device is going through different scenarios. So that's the step 3 that he does. First is, once I created the virtual devices, test cases, I run them again in a manual testing fashion using a UI or in an automated fashion using API, and I verify it on the cloud. And from an automated verification standpoint, because these tests are also running in an automated fashion, the guy could actually use a Selenium or a APM that are known in the web and mobile world to get these validations automated. Now, so that's from a functional standpoint. But the IoT testing also has the need for testing things at scale, because stuff always works with one device, 2 devices. But when you throw thousands and hundreds and thousands of devices at them, you see different kinds of failure happening at different points. Be it the gateway level, be it the network level, cloud level. So the next thing is the need to be able to do all of these things in a virtual world, but with hundreds of thousands of devices. That's where we said, being able to do something like this on a virtual machine, on a PC that we used to do in the past, or even in a data center, in a private data center, is not going to work, because you have a need to, as you scale up with thousands and millions of devices, you also want the test infrastructure to scale up and scale down to come up with these devices. So then we said, okay, this test bed not only does all of this, it also has to work in a cloud in a completely scalable fashion. So the tester could test with one device or a million devices as he wants. Right, so that's the overall high-level architecture. Replace the physical device with the virtual construct, and then have them pump data for different scenarios, test it up. But it doesn't stop there, right? So we started with the virtual device, having the view of the cloud is where everything happens. Cloud is the most intelligent thing, so the device can be completely simulated from a testing standpoint. So if we were to take the example of this telematics environment, it's a sliced one for the sake of simplicity. In this case, this device is getting connected to the truck. This is tracking speed, RPM, fuel level, and the GPS location, and is sending it to the cloud from an onward telemetry perspective. And this device also supports controlling this device in terms of locking it, unlocking it from a remote fashion, right, using a mobile app. Now, one has to test it with the virtual device. What they do is they create something called a data Doppel, which is a 100% simulated device in our platform. So first thing, you map all the data points that you are and the commands that your device is handling. So you have a one-to-one mapping. It's all created using the UI. I'll show you shortly. Second, you stitch together simulated scenarios using the library functions that you provide. Again, as I say, library function, you don't need to code. This is all, again, a low-code UI that you do. The library function also takes into consideration the dependent variable, etc., right? The GPS movement is based on speed, engine RPM is based on speed, so on and so forth. And you also configure the other things like the payload formats that your device will handle, the different kinds of protocols that your device will handle, MQTT, HTTP, WebSocket, so on and so forth. And finally, the test devices, even if it is virtual, they have to have the same security characteristics, right? They have to have a device ID whitelisted from your cloud. They have to have a certificate that is whitelisted from your cloud. So in this case, you create a completely virtual device by configuring all of these aspects using the UI and simulate the data points and commands. Now, not that, you could also simulate the network communication that is happening between these two instances, because a lot of application behavior is based on the data that is being received. So in a real network environment, some data could get dropped, get lost in a protocol like MQTT. And in some cases, there could be a duplication of data that is coming in, delay that is going on, etc. So you will be able to simulate all of those aspects with the simulated device. But then the focus of testing here is the applications on the cloud. But then the guys came back to and said, it doesn't stop there. In reality, though, all of these devices are more intelligent than just taking the data and executing commands that are coming from the cloud. They make decisions locally, which means I also want to be able to test those decisions that are happening locally. So then came up with the other variant of these virtual devices or Doppels, what we call the VM Doppels, which helps people do the edge application testing, the application that is running on the device. In this case, though, rather completely simulating the device, what you enable the tester to do is to take the software that is running on the device, drop it into a specialized virtual machine that we offer, which supports all the IoT related CPU architectures, right? Intel 3264, ARM 3264, etc. And then feed it with simulated inputs very, very transparently, right? So the modeling exercise goes similar. You configure the data points, etc., simulation functions. But in this case, you don't need to configure anything else. Take the software, drop it in, and the software, when it is running in our special virtualized machines, whatever data they try to read. Okay, I'm reading a GPS location. I'm reading the speed from a canvas. Everything happens from a virtual entity. So enabling the tester to control everything that the software reads and then behaves from there on, which means the guy could now simulate everything, test the software on the device as well as on the cloud, end to end, including the network behavior, which I said by throttling the network at the layer 2 level, losses, retransmit, so on. But then one catch here, right? When Vinay talked about, he showed a big stack of things in IoT. At the ground level, it starts with the physical device, and then on top of it is the software, and then the different layers of software from different people, etc. The hypothesis that we have taken, or the conscious decision that we have taken, is we will enable in our platform, in the virtual testbed, people to test from the software layer onwards. We will categorically keep out the physical hardware and firmware out of this whole thing, because those things needs to be tested with the hardware. I mean, if it is a sensor sensitivity, if it is a radio sensitivity, you need to test it with the hardware. So the philosophy that we go with is, the 15% of your whole thing that needs to be tested, they are all hardware dependent, environment dependent. Continue to test them the way you are testing it today, in a field test manner or whatever way it is. But then those layers don't change week of week. What changes is the entire application layer on top of it. So we let you test the rest of the 85% of the software stack in the virtual environment, thereby allowing you to be multifold faster in your endeavors of launching this product, and as well as reducing the risk when it gets into production. Now I talked about it in the previous case. It's a simple single device case wherein you mount a device to a truck sends the data to the cloud and decisions get made. But real-time IoT solutions are much more complex. They are a combination of many such connected products coming together. For example, a connected warehouse. Connected warehouse involves data from a connected truck, the data from the forklifts and cranes and everything else that is going on inside the warehouse, etc. So, in which means you have multiple connected products pumping data to the cloud and working together to bring out a value proposition for the customer. So, the virtual testbed, especially the Doppelio, should also allow you to do this multi-device system of things configuration and simulate scenarios around them. So, in our platform, we let folks do this as well, not just single devices. Now, quickly moving on to the case studies, we have been doing work in across multiple verticals. The most exposure had been to the automotive. I would like to present 3 cases here. In here, you see, first one is a tractor as a service platform, wherein the customer was moving to a different business model based on the telematics platform that they had. The testing challenge, they had to do a lot of field testing every time. They needed to improve the lab testing coverage. They were able to do so to a large extent using Doppelio, thereby being able to accelerate the time to market multifold, right? A sprint on sprint, they will spend one sprint completely for testing. And with Doppelio now, you don't need to do that. You can finish the entire testing for the sprint sitting right at your desk by allocating a couple of days. And then the second one is a validation of a FOTA subsystem, wherein the software had to be validated. There is an intelligent software stack running on the device as well as on the cloud, and then they had certain constraints with doing them faster, comprehensively, etc. So this one, as well as the next one, which is a connected car platform, which is having a very tough deadline in terms of the launch date, with a certain scalability as well as set of features, as well as the requirements of enhancing them continuously. So I will have Pramod, who is from Bosch, who is a first-hand user of Doppelio for these 2 environments. He will talk about it in detail. So thereby, what we are able to do with the virtual testbed in all of these cases is first, reduce the risk of failure when the product gets launched in the production. As I mentioned, even if you do field test, you're not sure that you have tested everything because you cannot control the environment. Whereas in the virtual test bed, you are able to do so. First thing, being able to reduce the risk of failure. Second, now because it is all software, on the click of a button, everything happens. You are able to validate things faster and early, accelerating the whole exercise of time to market itself, and thereby as well reducing the cost of quality. The direct one in terms of the effort spent, and also the indirect one in terms of finding and fixing the defects much earlier in the life cycle. Moving on, little more details on the connected tractor of the as a service case study. This is a case of OEM, off-highway OEM, who is focused on agriculture vehicles as well as construction vehicles. And they were trying to do a lot of value-added services on top of the vehicle that they sell, as well as eventually transform their business model from selling the vehicles to renting it. And then again, in this case, again, multiple layers of teams are involved. The guys from the hardware, the guys from the telematics software team, and then the guys from the business team, the application team, so on and so forth. And the one requirement that the business has given to these IT teams or the head of IT is, whatever you guys do, release into production, I want a 95% accuracy and reliability. So I'm sure that I'm not going to be losing money on my product when I put it out there. Now, in order to give that confidence to the business, right, what it means to the IT teams that are building this product, right, they are dealing with complex algorithms to compute some of the decisions that this platform was taking, dealing with multiple streams of data. In IoT, we don't make decisions just by looking at one data point that we came, right? For example, take the example of fuel preferage, that suddenly there is a huge drastic drop in the fuel level in the vehicle, which means somebody could be sucking it out, which is a very real problem in the vehicle environments. But now I cannot just say that by looking at one data point, because the same behavior happens when the vehicle goes through a pothole, right? Suddenly your vehicle tank shakes, and then the system reports a dip in the value. So you need to be looking at 5 minutes of data, 10 minutes of data to say something happened, and just not data from one sensor, but from a multitude of sensors to call it a decision. So that's from just simply data and decision perspective. But then the off-highway vehicles have other complexities, right? You run a vehicle. You would have experienced it when you're driving around your vehicle in highways, right? A lot of times your Google Maps does not work. The very reason being the mobile app is not able to get the GPS fix because there is no satellite visibility there, which is very real in off-highway vehicles, right? They can't get GPS fix. Similarly, network. We don't have network reliability everywhere. Now, the application that they are building has to work with all of these complexity. That's easier. But then when it for the testing guys have to test for all of this complexity and to certify that this stuff works. Case in point, in this case, right, is the key feature called Acreage, which is responsible for figuring out how much work that a particular tractor did on the field from a utilization perspective. Now that calculation depends on the size of the tractor and the implement that is fitted to it, because this will decide how much you should move inside a field and how far you should move. Then the second in the same lines is the shape and size of the field, which means the guy who's testing this feature has to test it for all of these different combinations, which are not even relevant to the application code. And then comes the things that are relevant to the code, right? I'm testing in, but then when I change the speed, the resolution, spatial resolution of the data that I capture will change. The guy has to test for it. Similarly, the other functions that compute different other things, etc. The conditions of GPS unavailability, network availability, so on and so forth. So this 95% is just not easy, right? So when we spoke to them, their plan was to start saying, oh, we will do, the first round of testing, whatever we could do in the lab. Then we will allocate a couple of months for testing it on the field. So the testing team, a couple of them go to the factory, book the machines and drivers, different kinds of them, go test it out. And even then, from a project management and a QA management team's perspective, they had questions from all QA metrics, right? Time, effort, cost, quality. None of them was very objective and clear what will be achieved at the end of wasting so much time and money. So when we spoke to them about Doppelio, where they can create a virtual tractor, they don't need to be going to a field and run the tractor. They create a virtual tractor, point a field in on the Google Maps and drive it whatever way they want, in whatever speed they want. They were the first takers to go with it, right? So if you see the screenshot that you see here is one particular testing scenario where they virtualize the tractor, choose this particular field near to the factory because they wanted to be real. And then they said, okay, I will drive the vehicle from here to here in a certain speed. So now as they drive through the field, the vehicle, the device will capture the GPS location, all the other factors, send it to the cloud, and the cloud will connect those points to say how much work was it. And in this case, it was a very decent drive. The cloud connected it and said 2 hectares. The testing guy was happy, test case passed. He just tweaks one more parameter to it, which is speed. Now I am rather running it in 5 km/h. This is a very nice speed. It allows me to do my work faster. So I drive it at 30 km/h. Now see what happened to the system, right? Because the vehicle is moving fast, the device was only capturing GPS locations that are far away. And when the cloud application connected these two, they are up for a surprise, right? Because it only sees portion of the data, and it reported 1.2 hectare, which is about 40 to 45% of revenue loss straight cut. And they were able to do all of these things sitting right at their desk as part of the development sprint itself, rather waiting for the field testing time to come and then come back and re-engineer and all of this old stuff. This is the magic that they could do with the virtual testbed like Doppelio. Now I'll hand it off to Pramod to talk about the FOTA subsystem testing as well as the other case study.
Hi, I would just walk through a couple of, let's say, use cases that we have used or how we have used the Doppels to solve some of our problems in our connectivity programs. This first case is regarding the Telematics FOTA feature. This is a program that we run for one of the large customer based out of North America. So FOTA is kind of a, let's say, a fundamental feature for a connectivity program, probably the second most important after connectivity per se, because that is something which is used in a connected program to address any kind of problems with a connectivity. So if any problem is there with respect to reliability of FOTA, I think the connectivity program has a big question mark or a challenge, whether it is really connectivity. But FOTA per se as a feature has a lot of failure modes because it involves software running on the cloud. It also involves software running on the devices, and the device is subject to a lot of, let's say, system parameters like your network failures, corruption of your files, power failures, user switching of the vehicle. Yeah. So what essentially used to happen in this program when we were running is that these kind of tests could only be done by while running a vehicle test, and we know that all vehicle test is always going to be an expensive test, meaning that it used to take a, let's say, even to run a FOTA reliability test, it used to take a couple of days because we need to have a vehicle, we need to take it to a place where there are poor network areas to simulate that scenario and do a test. This would have been all right, not really a big problem if this test is something which we need to run once in a while. But FOTA is something which is fundamental to the program. So what it essentially means that every release of the software, even during the engineering phase, needs to be tested for FOTA robustness. Yeah. So then that adds to a problem wherein we have a scenario wherein our release cycles will get longer because we can't release the software without FOTA being reliable enough. So then we turn to Doppel, who has already partnered with us in another area to do a testing. Hey guys, can we actually simulate this scenario? Because finally the device software is nothing but how it behaves under different conditions, and can you work at this? So then we work together to identify both of these, let's say, test cases and try to simulate the different subsystems within the device software for a FOTA. Like we talked about the network test where you simulate a network on off, a pause in between are not available for a reasonable amount of time, and then this kind of let's say test scripts or test systems was provided to our testers where they could need not wait for a vehicle availability, but they can actually simulate this in their lab. So this internal helped us to basically bring down drastically our FOTA testing, and which helped made sure that every release was FOTA tested. So this was the use case where we used it effectively to have a faster release process and more reliable process. So this case is another program which we run for a large Indian OEM. So here, of course, the same use case which was applicable to the previous program was also applicable. But here I want to talk about another aspect of the problem that we faced and how did we solve it using the Doppels. Yeah. Here the challenge was that, of course, this is a connected car program wherein we are talking about the ability of the platform to support millions of vehicles on the road. And one of the key characteristics is the performance of the system at scale, whether the performance would behave the same when you have large number of vehicles running on the system compared to typically during your engineering phase where you have only few tens of vehicles. And the other aspect, which was something which we need to ratify during the engineering phase, was that what is going to be the cost bomb for the overall solution which we can provide it to the customer, and whether this cost bomb holds good when we are running a large number of vehicles. Yeah, so then we turn to the data doppels, which Rajesh touched upon earlier, and said that, hey, now it is basically, let's say, impossible where you manufacture even thousands of devices during the engineering phase, because that would basically involve a lot of cost, and simulating that on putting on a vehicle is an expensive exercise. Can we take this device onto the cloud, where the amount of scaling of the vehicles is basically pretty limitless, yeah, based on how much infrastructure you put it. So what we essentially did was simulated, and we vehicle basically in terms of performance is nothing but a data generator. So we have different data being generated and different frequencies, and this was taken as an input and formulated into a data doppel, which could be simulated for, let's say, 500,000 vehicles. And then this was used to simulate different kind of load profiles, which we would let's say experience in a typical scenario. Some kind of 100% devices connected to the same system, let's say 40% of devices connected to the same system, and then a spike. So different kind of scenarios we could test it. And what it enabled us essentially is that to identify our weaker areas in our target system, which will throw up only when you do a performance testing, and basically fine tune those part of the system. The other outcome was essentially was whether the cost bomb that we initially went ahead with, whether that cost bomb would basically hold well. Because if you see the table over here, any variation by 5% for a larger number of vehicles is a big amount of cost to a customer, and that is something which would not make anyone happy. Yeah. So in that case, this exercise that we did using actually simulating millions of devices really helped us to ratify whether the cost that we have presented to the customer holds good when actually you go towards the year 2, year 3 of your program, when you're talking about hundreds of thousands of vehicles on the road. Yeah, so that's what I wanted to highlight over here. Rajesh, over to you.
Yeah, thanks, Pramod. Okay, to summarize what we have seen so far, so I mean, we agree that testing IoT applications is extremely hard because of the dependency on physical environments and physical devices, which means virtual test beds are a must to be able to do the things faster, because that's the only way a company can be competitive and launch products faster against the competition. So, and which means you should be able to reduce the amount of field testing that is being done, increase the coverage on the lab, not just the increasing the lab coverage. You should also be able to increase the coverage of the test scenarios itself, the things that we're not able to do before, because you cannot do that stuff on the physical world. You should be able to add a lot many more number of test cases, thereby getting more confidence on the software being tested. And not just that, which is much more relevant now in today's world, where people cannot go to offices, people cannot work together, people cannot access hardware. Being able to test from anywhere, anytime, is also be an important characteristics that the virtual testbed offers to the testers. So three main characteristics. The devices are different from the user applications that we are testing, because they keep a persistent connection with the cloud. They do both the onward traffic, sending data to the cloud, as well as taking back information from the cloud, and they have a certain behavior or communication for different data points. For example, when I'm sending a periodic data, I send it in a certain way. When there is an alert, I send it in a certain way, etc. So the virtual devices that one creates needs to have parity with the real devices in terms of the behavior, and also the ability to test multiple scenarios in parallel, right? In a physical world, when the testers are testing with devices in parallel, and the devices themselves are going through engineering process, there is a huge scarcity of devices. And so the virtual devices should also solve that problem. I should ideally be able to throw more people at my problem and finish the testing as fast as my business needs. And that comes in extremely handy when you have the virtual devices. And in case of Doppelio, we call them Doppels, which in German is the name for twin, right? And then the second aspect, as I talked about, is the simulation of scenarios, test scenarios around the virtual devices. The biggest difference here is not being able to simulate the scenarios that you are able to already do in your lab or the field, but the ability to do lot many more variations of the scenarios, because IoT, it's not about always 1 + 1 = 2. There are a lot of variations that happen to it, because the sensors misbehave in completely unexpected fashion, network misbehaves in completely unexpected fashion, so on and so forth. So the test scenarios has to be brute force driven, have the boundary conditions, and between these boundary conditions and above and below the boundary conditions, I should be able to do lot many or as many variations as I can do, so that I'm confident that my stuff works, right? So that's the ability to create and do unlimited data simulations, again, subject to the parity with the device behavior and environment behavior. And last but not the least, if it were to be an engineering exercise in itself, where somebody would have to, sit and understand the whole thing of physics and chemistry, as well as, do a lot of code, it's not going to work, because when it comes to connected systems, things move much faster. The business teams are looking at doing and releasing these features like they would develop a mobile app, right? So that's the kind of speed, which means all of it has to be extremely quick in terms of being able to do this. So that's where the low code automation comes in very friendly. Even if you are a manual tester, you should be able to use the product, switch to the scenarios, quickly test it out, and run them, on demand, right? Not just at the end of the sprint, but sprint on sprint as a regression exercise. I want to be able to do without having to do a lot of work. So that's the low code automation part of it, and thereby finally enabling the testers to do better test coverage, keep helping the business to be more confident. Second, doing the things extremely faster, right? Because when a guy tests a mobile app, he is actually testing like an end user. But when a guy is doing a device testing, he is mandated to behave himself or behave like a device, which is just not intuitive for a human being. It's extremely hard. People find it extremely hard, and because of that, defects get skipped. And with a simulation environment like this, the testers will be extremely productive, concentrating more on the scenarios and than the process of execution. And last but not the least, is the thing of reducing the vehicle tests or field tests itself. Thereby reducing the cost of the testing exercise, as well as the going on the effort that is required to go on the field, etc. So now I'll take the next 3 to 4 minutes to do a quick demo of what I talked about in these slides, right? So I talked about two kinds of Doppels. The first one is the data Doppel, which is the 100% simulation of, and then the second one is the VM Doppel, where we took the software on the device and then let you run it inside a virtual construct, right? And I will show you the whole process that is driven using the web UI. So now the main the point of interaction with Doppelio for the tester, as I said, is the web application. So this is the console that that one gets to see after logging in. The first construct is the Doppel model, which is the virtual model of the device for the device that I had on the slides. This is the model. So wherein I said the first thing they would create the data points, and then they would attach some simulation functions to it, etc. So this is the first thing. Second, once you have created the data points by clicking the button and feeding in some details that you already know from your application spec. Second is the configuration of the payload formats. In this, I have a sample of 3, but in a real world device, you have like 10 or 15 or 20 different payload formats. As you see here, this is a device that does JSON-based format communication. So here you have a JSON with the keys which are constant, but the values which are variables, which gets populated at runtime as the simulation runs and gets packaged and sent to the cloud. And where it gets sent to the cloud, we define it using a construct called channel. So in this case, for demo purpose, I have a lot of them, but primarily in the workspace, the TB telemetry is associated with an IP address and port number of an MQTT cloud server that is listening for data from the devices. And this one speaks the protocol of MQTT. So I have an additional configuration for the payload, the topic name, etc. So then the next one, and then this device, as I said, is also taking the remote commands for locking, unlocking. So there has to be a mechanism where it subscribes to the commands, and then there is a command handler for each of the data that gets coming in the subscription topics. In this case, it's a remote lock unlock. So the guy looks for the command lock command. The virtual device is supposed to acknowledge it when the command is received, as well as change its behavior to a locked state because the cloud said the vehicle should get locked, so on and so forth, right? So this is the modeling of a simulated device at the high level. Now, if it were to be the VM Doppel, or the Doppel that runs the actual device software, you mark it as a VM Doppel while creating the Doppel using this UI. And then you essentially associate the package, which is the device software package that is uploaded using a different workflow into the Doppel model. Now you don't need to configure anything else, because everything else is already coded up into the device software. You put it inside it, run it, whatever the device software reads from all of these parameters, everything is going from the simulation environment. Step number 1. Step number 2 is to create specific test devices from that for that model, right? So for example, I have 5 testers, so I want 5 different devices with different device IDs that is whitelisted in the cloud, etc. So I've created a test device. I can create any number of them, right? In this case, I've got like 3 of them. And if I'm doing a load test, I can't be doing, creating devices one by one by, manually feeding in the data. I need an automated way. So what we enable the customer to do is to whitelist thousands of devices, create a CSV file out of it, upload them directly. So you end up creating what is called a Doppel group, which is a combination of many devices that can be used for load tests. Now, the step number 3 is the creation of test scenarios itself, which are test cases in Doppelio. I wouldn't go into the details. In this case, a test case is a scenario behavior of the device over a certain time period, changed in different time segments. For example, in this case of a truck, there is an ignition on cycle wherein some parameters has to be changed exclusively. There is a ramp up cycle where the speed has to be changed in a certain way, etc. So the test steps allow them to change it whatever they want. Now I'll quickly execute this and show what it looks like in reality, right? So executing this, driving the vehicle from point A to point B in a good network is like this. You go click the run button, pick up one of the instances that you created, device instances, Doppel, and you click run. And the cloud is bringing up the virtual device. Now in this case, this is a demo application that I've got, which is receiving data from the virtual devices, and it is dashboarding here. In a real testing environment, the customer will have their own application here, which is dashboarding, and then the tester would verify things like, okay, my dashboarding is happening, alerts are happening, so on and so forth. So in this case, what you see here is the demo truck test case that I ran. The truck is moving in from Electronic City, Bangalore towards somewhere in Mysore Road. And then it is also pumping the speed curve that the guy is simulating, the RPM, which is dependent on speed, the fuel level, so on and so forth. And it's also for demo purposes. The sequence number of the data that is coming from the device to cloud is being plotted here, which is a continuous curve. So this is one good test case. Right now, if somebody wants to create variations of this, it's all about saying, okay, copy the test case, give it a name, and then change things around. Now I don't want the vehicle to do this, but then I want to do something else, etc. So I can go to a test case, step, change it, change the values, add fault conditions on data, network, etc. So, and also remove some steps, add some steps, all of that easily by cloning and changing. Now I have created like that a copy of the good network test case, but then I wanted to add a network fault. What happens in certain segment of the vehicle movement, the network goes away. How does my application behave? Now what I did, I went to this steady step, added a network fault here. I said, drop all of the packets that is going in during this segment by doing click add, network profile. I say drop fault, 100% of the packets, right? Now I run this test case. Look at what happens magically. The same truck. Now you'll see the truck restarting from Electronic City again and starting to move. You see the data being reported in the initial phases ramp up curve because the network is still available. So you see the sequence number behaving exactly the same way like the previous run. Now you see it already flattening out because the network is not there, device is not able to send the data even though it is generating it, and the application is suddenly clueless. Now after some time the network got resumed, and then the application is suddenly starting seeing the data flow. Now in a real environment there are going to be verifications associated with this behavior because there are decisions that are happening in real time, which now the tester is able to say, okay, it happened, pause, didn't happen, fail. Now it doesn't stop there. If it's a fail, it goes to the dashboard. You can now look at what exactly happened. Is it a real failure or it's a testing problem, right? So he has a dashboard where you can completely see all the data flow between the device and the cloud. Here I have only the out, but all the in and out communication that is happening with the device is available. So we can download it, attach it to the test case, give it to the developer and say, this is exactly the sequence, exactly the data, there is a problem, please take a look at it. No more questions, no more arguments. And in real time, you can also see the simulation, right? I mean, I was simulating a speed curve, so you can see all of this happening in real time. So this is how a functional test gets quickly created and executed on the click of a button. Now, if it is a load test, it's not very different, right? I take the same scenario, rather running it with one device, I just say I want to run it with 1 million devices, and I choose a Doppel group instead of the Doppel, and I click run, and suddenly or magically in the backend, Doppelio brings up 1 million trucks, runs them under this scenario, and all of them are communicating concurrently or in a phased manner, whatever way the tester has set up, with the cloud, enabling them to do very realistic testing of their environment. So this is a load test, and I said, oh, this is all manual. I mean, the device execution side is very well automated, but I want to do automated regression suite, end-to-end validation, where I want to also validate UI and stuff using the test engine. So what you do, you work with the Doppelio APIs, api.doppelio.com. Everything that you were able to do using the UI, you are able to do using the APIs now. So what you do is, one side, instead of going and clicking the run button, etc., you create a script that is invoking the Doppelio API to run this test case, nothing beyond that. And when the test case is running, go check whether the point that is supposed to happen here is happening, your mobile app is receiving alert, etc., using the REST, the mature frameworks like APM or Selenium or whatever is applicable for the actual application. So that, ladies and gentlemen, is a quick overview of the innovation that we have done in terms of bringing up a IoT specific testbed, taking into consideration the characteristics of connectivity, the edge and cloud, and the nature of the testing itself, testing and the nature of the testers who are involved in this whole exercise. So that was a quick brief from my side. Thank you very much.